An alternating series is one where the terms jump between positive and negative. And it has to be positive, negative, etc. You can't have, say, positive, positive, negative, positive, negative, negative. It has to be always switching back and forth for each consecutive term. And so, an alternating series has one of two forms usually. We have some general term here, and then a negative one to the kth power or the k plus 1 power. And that's what makes it alternate. And if we have an alternating series in one of these two forms, then we can test for its convergence. If the general term here is always decreasing as n goes up, and also the limit as k approaches infinity of this general term is 0, then the alternating series converges. So, and if we know that if the limit is not 0, then it will diverge by the nth term test, not the alternating series test. So, for this series here, you can see that we have a general term and then the negative 1 to the k plus 1 power. So this fits the form, one of these two forms here. And just by looking at this, we know that this is always going to be decreasing since we have k on the top and k squared on the bottom. But if you wanted to prove that, then you could take the ratio of consecutive terms, a of k plus 1 over a of k. And you'd find that the ratio is always less than 1. So this proves that the terms are decreasing as n goes up. So that's the first condition of a test. Now the second one is taking the limit as k approaches infinity of the general term. And since it's bottom heavy, the limit is 0. So this series fits both conditions of a alternating series test, so it is convergent. And this is useful because, obviously alternating series involve negative terms. And all of our tests so far, or most of them anyways, only worked if we had all positive terms. So we can also find the error in approximation if we use a partial sum to approximate the actual sum of a convergent alternating series. So the sum, the real sum, is always between any two consecutive partial sums. And if we use a partial sum to approximate the real sum, then the absolute error, the sum minus the partial sum that we use to approximate, is always less than or equal to the general term of n plus 1. So say we use the fifth partial sum to approximate the sum of an alternating series. Then we know that the error in approximation is less than or equal to the sixth term in the series. So if we have this alternating series, this is the alternating harmonic series. See, it's 1 over k plus this negative 1 term. So say we use the eighth partial sum to approximate the sum of this. So what would be the error? Well, if we use the nth partial sum, the error is less than or equal to the n plus 1 term. So the ninth term over here, which is just 1 over 9. So when we use the eighth partial sum to approximate the sum of this alternating series, the error is going to be less than or equal to 1 over 9. So that's how accurate we are. And so if we have a series and we can prove that it converges if we take the absolute value of the general term, then it converges absolutely. And if the series of absolute values diverges, then the series diverges absolutely. So here again we have the alternating harmonic series. So if we take the absolute value of this, then it'll just be the regular harmonic series, which we know diverges. So this alternating series diverges absolutely. However, this alternating series is actually convergent because the terms are decreasing and the limit as k approaches infinity of 1 over k is 0. So it passes the alternating series test for convergence. So this alternating series converges, but diverges absolutely. Here we have a series that alternates between positive and negative, but it's actually not an alternating series. First of all, we don't have the negative 1 to the k power. And second, if you actually test integer values of k, you'll find that it doesn't switch from positive to negative every time. It'll go positive, negative, negative, and so on. And so, if a series converges absolutely, then it also converges normally. So to prove that this converges normally, we're going to first prove that it converges absolutely. So taking the absolute value of this general term, we know that it's always less than or equal to 1 over k squared, since the cosine function ranges from negative 1 to 1. And if we take the absolute value of that, it'll always be from 0 to 1. So it never goes above 1. And well, we know 1 over k squared is just a p-series with p equals 2, so it's convergent. So using the comparison test, a bigger series converges, meaning a smaller series also converges. So this absolute value series converges, meaning that this original series converges absolutely and therefore converges normally as well. And if we have a series that converges normally but diverges absolutely, such as the alternating harmonic series that we saw earlier, then it's called a conditional convergence. So over here we have an alternating series, and taking the absolute value of this general term and then simplifying it some, we can say that it behaves like 1 over k. And so we do this to use the limit comparison test. So using the limit comparison test with 1 over k and the series of absolute values, the limit evaluates to 1, which is finite. So these two series have the same convergence or divergence. And since this is the harmonic series which diverges, this series of absolute values diverges as well. So this original alternating series diverges absolutely. But if we use the alternating series test, it will converge regularly. So it converges normally but diverges absolutely, and therefore it converges conditionally. And we also have a ratio test with absolute values. So just like the normal ratio test, if we take the ratio of consecutive terms and the limit of that as k approaches infinity, if the limit is less than 1, then this converges absolutely, and therefore converges normally too. And p greater than 1 means the series diverges. And if p equals 1, the test is inconclusive. So here we have an alternating series, and taking the absolute value of the general term, and then taking the next term, u of k plus 1, we find the ratio of these two. And then taking the limit of that ratio, it turns out to be infinity. So this alternating series diverges by the ratio test for absolute convergence.